It's okay? Okay. So, yeah, I'd like to thank the organizers first to give me this opportunity to present our work here. I'm working with Professor Adriano Fontana and Dr. Emiliano Merlin and Dr. Fernando Caro at the Observatory of Rome. And so let's start. Um, so the first thing that I'd like to say is describe the problem that we're trying to solve, and it's called blending. So here you are, this eye is your line of sight, and you see a galaxy at redshift 0.1. So is there a pointer here, do you think? Okay, yeah, okay. So this is the galaxy that you see, and this is just a segmentation map. So it's just describing where are the significant pixels in this image. So you see another galaxy, that's at redshift 0.2, and it's also in your line of sight, but they're not physically interacting. But it does create a problem, which is this confusion effect. So what you end up seeing is this galaxy. So you have significant pixels from one and the other, but there is also a certain area of overlap. So this is blending, and we want to try to solve this with machine learning. So why do we need to do it anyway? Because we need accurate flux measurements. This is needed for all sorts of things like accurate measurements on masses, distances, and so on. We also need to know the shape and the light profile itself. So not just the measurement of the flux, but the distribution of light in that galaxy is also needed for template fitting codes like TFOT, which do aperture photometry. And it's also important because with upcoming telescopes like Euclid, we expect this blending fraction to be really high in the dense regions. So it's not a problem that we can just ignore. Oh, thank you. Thanks. Okay. Sorry, is it this one? Oh, yeah. Okay. Whoops. Okay. Yeah, so 50%. So it's not something that we can just ignore. We want to solve this problem. And there is a standard method that's called SExtractor. So you have this image that you saw just like a slide ago. And if we have this sort of structure where you know where the overlap is, then you can solve this problem quite well. But what SExtractor ends up doing is just assigning each pixel to either one or the other, because it's based on like some threshold methods. And so what happens is this one is going to be overestimated and this one is going to be underestimated. So it's always a problem to deblend with SExtractor. So we want to use autoencoders. And I'm just going to go quickly because this has already been covered in some of the talks. So you have an input X and the outputs Y. And the goal of an autoencoder is simply to reproduce your input as well as you can. And it's made out of 3 parts. So there's the encoder that basically does the dimensionality reduction. There's the decoder that will reconstruct your input. And the most important part is this latent space. So this is called the bottleneck. This contains the encoding of the features that you learn that the encoder gives you. So we also use variational autoencoders, and very quickly it's just sampling this latent space from a Gaussian distribution instead of just one-to-one mapping from the input to the latent space. So there are 2 VAEs that we need. The first one works on only single galaxies. So this input has just one galaxy in the image. And what this is trying to do is reconstruct the inputs very simply. The second one will take the decoder from the first one, and the weights are then fixed. So you don't train for the decoder anymore. Your input becomes this blended pair of galaxies. So you can see that there is 1 and 2. And what you're essentially trying to do is trying to map this to a point in latent space such that when you use this fixed weights decoder, you try to go as close to the original galaxy without blending. So this is how it's going to deblend the galaxy in the center. Okay, so we have we've tested this with analytic simulations that were created with ECK. This is a code that generates mock galaxy catalogs with realistic positions and stuff like that. And so we do this for Euclid visible band. We make some masks, which are sort of physically motivated. Because if you have a galaxy that's really, really bright, then if you have blending, then it doesn't really matter that much if you deblend them or not, because the error is not going to be that great. And also, we want to constrain how much data we have with simulations just to test if it actually works with realistic amount of data. So the stamps are created using Galaxium, which is an image simulation toolkit. So it's going to take your parameters that you got from the mock galaxy catalogs and give you an image of a galaxy that follows those parameters. So these were about 250,000 galaxies, and we subsampled from that and ran our algorithms. This slide was just to tell you that we wanted to check with simpler simulations, but because there's a time constraint, I'm not going to show you the results from this, because there is a more interesting data set that we worked with, which is the realistic simulations. So Euclid is not yet launched, so there are no real images from Euclid. So this data comes from the Euclid Morphology Challenge. That was a collaboration between teams from Italy and France. And it has 5 fields of 0.1 pixel scale, and that corresponds to about field of view of 0.5 square degrees. And it has about 70,000 objects per field. So how were these galaxies made? They were also made with a variational autoencoder that was trained on the Cosmos field. So those galaxies are real. And then there's a normalizing flow that's trained on the latent space of the VAE. So it becomes like an emulator. You can give it an input. You can say, oh, I want a galaxy that's this big or this bright. And it will give you a realistic looking galaxy with this VAE plus normalizing flow setup. So then to make it like a galaxy that you see with Euclid, you convolve it with the PSF. So this is like a signature of a telescope, and it's going to tell you what the galaxy will look like if Euclid was actually observing it. So here are just some examples of what these galaxies look like. So you can see they're not super symmetric, and there are like faint twin structures and so on. And so this is why this was the more interesting data set. Okay, very quickly, I'm going to tell you how the data is distributed. So I said there were 5 fields of about 70,000 objects. So 1/3 goes to the first VAE that works on isolated galaxies, and 2/3 goes to the blended galaxies. And for each of them, 80% is the training data and 20% is the test data. So these blended pairs are made simply by taking a galaxy in the center, placing another one in an annulus around the center, and then you add the fluxes to get your blended pair. Okay, so now we're going to look at the results for the first VAE. And this is what it looks like. So you have the input, which has some noise. And this is the true like test image. And this is the prediction by the VAE. So for a really faint galaxy, the VAE doesn't really do super well, although it's able to get some information about the flux and the size of the galaxy. But as we go brighter and brighter, the VAE does much better than the other cases. So let's look at the flux estimates. Here on the x-axis, you have the flux from the test image. That's just estimated by summing the pixel values because the test images are without noise. And here you have the prediction from the VAE. This also, you can just sum the pixels because the VAE is also like a natural denoising algorithm. So there is a one-to-one correspondence and the errors are acceptable in terms of the standard errors that you get with SExtractor. So it's 16%, and we're going to look at next the results from SExtractor. So SExtractor does much worse than the VAE. There is a strong bias, and there's also many cases where there's 100% error, but in general, it's not doing too well with fainter galaxies. So we can look at some examples of why this is. So when you set the number of objects to be 1, so you run your SExtractor run for all of your objects, but then you only make this plot for objects where SExtractor found only one galaxy. And then you make this plot and it becomes a little bit better, but it's still quite biased. So this is an example of when SExtractor finds a single object. Here is the test image. This is the prediction by the VAE. And we can see that the segmentation is really quite little. And this is why SExtractor is underestimating the actual true flux. So another case is when SExtractor doesn't find an object at all. So there is no segmentation. And these are the cases where the error is 100%. So sometimes it will also find 2 objects, even though there's only 1. And this is because, I mean, also to just like the human eye, you can kind of see that there are 2 distinct structures here, but this is sort of like the wing of the galaxy. So here, what happens is that the central one is going to be underestimated because a lot of the flux is going in the other galaxy. And this is why for all of these cases, you have SExtractor performing much worse. There are some cases where it does better than the VAE, and this is because it encapsulates a larger area of the segmentation map. And this in general is something that's not working with the VAE, is that it doesn't really focus too much on an area outside, let's say, the mean area of the galaxies. So maybe we can change something here. But this is a comparison of the results from the VAE and the SExtractor. So there were 15,000 galaxies in this test data set. And 80% of the cases, VAE outperforms SExtractor. For the rest, where SExtractor does a little bit better, where the galaxies were really bright, even then the error on the flux is not super bad. So it doesn't do too bad, but it's just SExtractor outperforms it in those cases. So now we're going to look at the second part of the algorithm, which actually does the deblending. So again, this decoder is fixed, and you have galaxies which are blended as the input here. Okay, so first case input, this is the test. So the true central galaxy before blending. This is the prediction from the VAE. The second case, you can see 2 distinct galaxies. And the third case, you can see a fainter galaxy in the center. So the VAE doesn't do too badly, but it's not great all the time. So it also depends on what kind of blending there is, what level of blending there is, and we're going to discuss that in the next slides. So this is an overview plot of the flux from the central galaxy and the one that's predicted by the VAE. There is a 1-to-1 relation, but there is a certain bias at low and high magnitudes. So about 20%, which is acceptable. Okay, this is what SExtractor does. So it's just going all over the place. And we can look at some examples of why it's doing so badly. So if you consider all the data points, the standard deviation is like 100%. So this is complete rubbish. So we have to ask, okay, which are the cases where SExtractor found only 2 objects, even though this is not information that you will have in real cases, but just for comparison's sake, like we select only the objects where SExtractor found exactly 2, and then we see that the standard deviation is about 30%. So it's still worse than the VAE, but it's not as bad as before in the previous plot. So as I was saying, that there is certain complexity that's involved in blending. So we have these 2 arbitrary metrics. So one is this blended over central galaxy area. So the overlap area over the whole area of the central galaxy. And the other one is the flux ratio. So how bright one is compared to the other. So we have here we have a galaxy that's much fainter, so the flux ratio is smaller, and also they're quite far apart. So, and then we have the same two galaxies, but much closer. So now the area of overlap is increased. So this is a much more complex case to solve. Then we take a galaxy in the center that's more brighter, and you can imagine why it's easier for the VAE to distinguish that there are two galaxies here. And again, it becomes much harder as you increase the area of overlap. So the final plots is here you have the flux ratio increasing, and here you have the area of overlap increasing. And we see that the VAE gets worse as we go in this direction as we expected, and gets worse in this direction as we talked about before. This is the result from this SExtractor on the same images. So it's doing really poorly. All the blue points are the cases where it detected exactly two objects. The green points and there's another color involved is for 3 or more objects, or less than 2 objects. So if we again look at points where it only found 2 objects, we see that for smaller blendedness or small area of overlap, SExtractor is not doing so badly. It's still worse than the VAE, but it's not totally, spitting out rubbish. But here, really, when it's the area of overlap is really a lot, then you have SExtractor failing badly. So there are other things that we try. We do hyperparameter tuning. So you want to optimize the size of the latent space, the number of layers, and the loss ratios, because you have the KL divergence loss and the reconstruction loss in the VE. There are also things like learning rate schedulers involved. So every time you want to change the weights of your network, you make a certain like delta W, and this you can keep changing so that it converges faster and so on. There's always a limitation on how much real data you're going to have that's going to be useful. So you can augment them with flips and rotations, because the galaxy's properties are essentially going to be the same, but you have another data set that way. We also want to include something like custom losses. And as I said, it's because it looks like the VA is only working really well in the center. So if we could do either higher weights in the center or vice versa, depending upon which part of the galaxy you want to focus on, either the wings or the center, we can try to increase that accuracy. And the final goal of the work is to make a pipeline for Euclid images. So once you have real data, you find which galaxies are isolated and which are blended, and then you train on the isolated galaxies, and you can deblend the others. Yeah, thank you.
Thank you. Very fast. Question?
Oh,
nice presentation. Just a curiosity, did you try to evaluate the estimation quality depending on the redshift?
Depending on the redshift?
Yeah.
No, we didn't. So
by evaluating the change in performance is by when you have more far or close to objects.
Yeah, but so blending is with galaxies that have a difference in redshift, right? So do you mean that when the redshift is between certain ranges and then no, we didn't. Okay. But maybe that's something that could be interesting to look at.
Other questions?
Okay.
You use the GalSim for simulating the galaxies, and GalSim produces very idealistic and unreal image of galaxies because it's pure ellipsoid and not twisting and so. So how do you deal with the fact that 99% of the galaxies in Euclid will be irregular, will be patchy, will be completely different, and then you have to disentangle, for instance, inside what looks like a blended image, a star-forming region into different parts of the galaxy. So how can you extrapolate the results to that?
So the test with the galaxies from GalSim was just a preliminary test. What we actually use is the realistic galaxies from, come on, from this. So they train on Cosmos field, and then they train a normalizing flow on the latent space. So you can tell which kind of parameters you want for the galaxy that you want to emulate. And so now you don't have ideal galaxies, you have wings and, like you said, star forming regions and clumpiness. So you have really realistic looking galaxies that have been Euclidized to test for if it's going to work for Euclid. Right.
Other questions?
Well, taking into account that she's using the B stand of Euclid, that is basically the mix of G, R, and I. So it is extremely noisy from scratch.
Yeah, that's still good. It would be nice to hear.
I have a quick question. So
Okay.
you are comparing the performance of your autoencoders with aperture photometry.
Yeah.
Now, have you tried fitting the galaxies, for instance, with the simple two-dimensional Gaussians?
Mhm.
That would improve with respect to the aperture photometry itself. So, of course, the variational encoder will be faster when you have to analyze, but just to see, since these galaxies are very small and marginally resolved,
Mhm.
so I expect that a fit with a two-dimensional Gaussian would not be that
Could
bad.
work,
Maybe
yeah.
better than the aperture photometry. Have you tried that?
I think it would definitely be better than aperture photometry, but maybe not as fast as the VAE.
No, of course,
Yeah.
of course. But
Yeah.
But
think-
I mean, the comparison of your encoder with the aperture photometry is a bit unfair because you know
But-
that you are going to do better.
But it is the standard method of deep learning still. I mean, this is what people use all the time, like SExtractor.
Not only that.
Yeah.
Yeah.
Yeah, maybe that's something that we could try as well. Yeah.
Of course,
have a
the
better
encoder will be
benchmark.
faster. That's for
Yeah.
sure. You
Mhm.
have to analyze millions, so you can't.
Right.
But just to check how your encoders performs, maybe you
Mhm.
could also try some tests on that.
Yep. Yep.
Okay, if we don't have other questions, let's move on to the last talk of this session. Thank you again